Right, so firstly the topic. Attractive fixed points. So what exactly is this? What is an attractive fixed point? Well, first we'll look at what a fixed point is. So, Justin, come on. So let me give you a little bit of an example to think about first. So consider the function f of x, let's say, equal to x squared. Something like this. Let's say I give the function the number 4. What does the function give me back? 16. Okay. Can anybody think of a number that I give to the function and the function gives me back the same number? Yeah, 1. So if I give the function the number 1, what will it give me back? 1. Any other numbers? 0. Anything else? No. So there's 2 special numbers in this case that I can give to the function and the function gives me back the same number. And this is pretty much the idea of a fixed point. It's a special point that doesn't change when it goes into the function. Okay, so if I calculate f of 1, I'll get 1. So like we said, put in 1, it gives me back 1. And if I calculate f of 0, I'll get 0. These are examples of fixed points. They are points that remain unchanged by the function. Okay, happy with that? A straightforward idea, I hope, yeah? Okay, so we'll give it a nice little box. So a fixed point, let's call it x0 of a function f is the point such that f of that point is still the same point. There we go. A fixed point x0 of a function f is the point such that fx0 equals x0. So what we're going to look at today is how you can find these points for the function f. Now, with the first example I gave you there, x squared, how did you find that? Well, all you did for it was solve it in your head. So like for example, in the function f of x equal to x squared, we just need to solve x squared equals x. Okay. Which gives x squared minus x equal to 0, because I just take the x over to the left. And then what's next? I factorize. And so I have x minus 1 times x equal to 0, and I get x equal to 0 or 1. Okay, now that's fine in this case, but what about if I had something like this? So what if my function was cos x? Could I try to solve it this way? Well, I could have cos x equal to x. So what would I do next? I could say cos x minus x equals 0, yeah? And then what's next? Well, I can't factor out x here, because one is x and the other is cos x. So you see, there's a problem there. I can't do it using algebra like this.
Can't you replace it?
Replaced by...
Because you know there was rules for trigonometry, like...
Yeah, we could try a trigonometry rule, but ultimately the problem is you're mixing trigonometry and algebra. You're having cos, and you could have sine and tan of x, and then you have x. Usually it's quite difficult to solve for x when they're mixed. If I had only cos x, you know, it could be possible. If I had only x's, it could be possible. But it's usually more complicated when it's cos x and x, or sine x and x, something like this, okay? So in this case, we see that our technique won't work here. We need something a little bit better. So what we're going to do is, we're going to try and use a method like yesterday. We're going to try and find a formula, a procedure, that will bring us closer and closer to the answer, like what we did yesterday. And in fact, what I'll do is, you can think of this finding of a fixed point as the same thing as finding a root. Because look what I did here in this example. I changed x squared equal x into x squared minus x equals 0. You see? So what am I looking for when it's stated like this? A root. So I'll think about it this way and see what I get. Okay? So, can I go on to the next page here? Yep, okay. Right, so if you want to find the fixed point, you're basically wanting to solve this equation. F of x equal to x. Now how can I change this into a problem about roots? Well, I'll just take the x over to the left. So on the next line I get f of x minus x equals 0. And now it's just a problem about finding the roots. But we just need to be careful here. What's the function in this case? No. The function is, no. It's a bit like this. Remember, when you want to find a root, you're trying to solve something like this. So actually the function here is f of x minus x. You want to find the root of this thing. Okay, so you have to be careful. The function in this case is f of x minus x. Right? Are we happy with that? Okay. So let me use the Newton-Raphson formula. Do you remember from yesterday? So you have the formula. The next guess, or the next estimation of the root is equal to our present estimation of the root minus, and then we have the fraction. Now what goes on the top of the fraction? The function. And then what goes on the bottom? The derivative of the function, yeah. So this is what the Newton-Raphson formula gives us, okay? So let's start plugging values in. In this case, what is the function? The f of x part on the top? Yeah, fx minus x. And then what goes on the bottom, in the denominator? Yeah, derivative, which will be f derivative of x minus 1. Okay? Happy with that now? Where's my 1 coming up? Right, now, you might say, okay, that's fine. And if you wanted to, you could actually use this. But I'm going to try and simplify this a bit more. Okay? It's fine like this. Like, it will still get you to the answer. But I want to show you with a bit of simplifying, you get this rather interesting formula at the end. Okay, so I'm going to simplify this a little bit. Firstly, I don't really want the minus out in the front there, so I'll bring the minus in. And I'll put the minus actually in the denominator. So I'll get rid of that minus in the front. And what I'll do is I'll change the denominator into 1 minus f derivative. Like this. Okay? And then the next thing I'll do is I'll split this fraction up into two pieces. So what I'll do is I'll take that top line out. Whoops. I'll take that top line out. Replace it by 1 and then put it in the front. Okay. So, yeah, you see what I did there? Yeah. Okay. Now, that piece there, 1 over 1 minus f derivative. Think about that as a bit like 1 over 1 minus x. And you'll have to think back to semester 1. Does anybody remember any formula for 1 over 1 minus x? And I'm pretty sure I told you at the time you'll forget it, if this helps you remember. No? Or maybe if I'll write it down here. So remember, or recall, 1 over 1 minus x. Nobody wants to try and tell me an interesting formula for this? I used long division to get it? No? It also comes up in sequence and series, geometric sequence, infinite sequence, no? Does this formula look familiar? No? Yes? Yeah, geometric, yeah. No, geometric, yeah. Yeah. Maybe if I replaced it with a different letter, like if I said or, maybe. So what type of sequence do I have on the right? Geometric. What's the A for this geometric sequence? 1. And what's the or? Or. Because I'm multiplying each number by or. And remember, you have your formula for the sum. It's A times 1 over 1 minus or. So here A is 1 and or is or. Geometric sequence. A whole semester ago. Yeah.
I skipped that question on exam or something.
Yeah, and now look at you.
Yeah, it was important.
It's important. I told you everything connects up, so it's important now. Anyways, we all remember it now, or at least sort of remember? Yeah, okay. So what I'm going to do actually is I'm going to use this formula in the piece at the end. Because if you look at it, it is actually like 1 over 1 minus or. So I can actually use this here. So I'll need to go to a new page. Well, maybe I can squeeze it in.
Sorry, Stephen, could you back to the 4th line?
Yes, just a second. Let me just put in now the formula at the bottom. It's plus, and then you have plus again, and then it goes on and on. Let's just see if that fits in. Yeah, there we go. Okay, so which line number now? The 4th line?
No, I think the 5th one.
The 5th one, yeah? What's the problem?
How do you move to this step?
Here to here?
Yeah.
Well, the capital F is like fx minus x. So these two things here, I'm thinking of them together as a function capital F. So on the top, I just have capital F, which is fx minus x. And on the bottom, I have f derivative x, which will be the derivative of these two, which will be derivative of small f, which is small f derivative, minus derivative of x, 1. Yeah, is that okay for you? Yeah. So now I have this result here. Okay. So I want to try and simplify this a bit more. I'll need to go to a new page, so can you write this down? being a little bit careless there. Those should be xn, of course, not x. It's not really a big deal, but I'll just put the n's in, okay? Okay, shall we go on? Now, before I go on to the next page, that infinite geometric sequence at the bottom, that formula only works when there's something particularly important about the geometric sequence. Does anybody remember? Like, I can't use this. Oh, very good. Yeah, you can only use it when r is less than 1. So, in fact, the moment I use that formula, I've now restricted myself to only cases where the derivative is less than 1. Okay? So I haven't said that, but I'm saying it now, that at this stage in the proof, I've now restricted the function to be a function whereby the derivative is less than 1. Okay? So we'll go on to the next page now, and I'll you just need to keep that in mind, actually, because that's important. Okay. So let me just get some more space here. Okay. There we go. And I'll just put up on the top here where f derivative at the point xn is less than 1. Actually, it could be between -1 and 1. Or the absolute of it is less than 1. So if you want to just make it a little bit clearer, -1, there we go. Okay, so let's continue now. If the derivative is less than 1, so let's say, for example, it's a half, what will this piece here equal? Derivative squared. It's not a trick question. A half squared? 1 over 4. And then the next term would be a half cubed, which would be 1 over 8. So what's happening to each term? It's getting smaller. So the square part is actually quite small if it's less than 1. Because once you square a number less than 1, it starts to get small very quickly. And remember, for numerical methods, you're not so worried about getting the exact answer. You just want a process that gets you closer and closer to the true answer. So in fact, if I want, I can drop all of these numbers here just so I can have a close approximation. So what I'll do on the next line is I'll drop everything after the square. Okay? Happy with that? Now I'll multiply out these two brackets and see what I get. So first I need to multiply by the fxn, and then I need to multiply by the negative xn. So first multiplying by the fxn, and then by the minus x n, and then minus x n times f derivative x n. Okay, did I do that right there now? fxn, yeah, plus fxn times fxn derivative, yeah, minus xn f derivative xn. Okay, happy with that? Yep, alright. Now, let me just copy this. We can see something cancels. What cancels here? There's two things that cancel. Yeah, the xn. And then let's see if anything else cancels. Okay, so now we have this. No, not the. No, that's it for cancelling. Yeah. Okay. But look, there's something in common at least. What's in common with these two? Yeah, f derivative xn. So I'll take that out. Okay, so you see I took the derivative out there because it was in common to both. Okay, happy with that now? Now, just to make it extra clear here, this is equal to fxn, whoops, plus, okay. You're multiplying two numbers here, right? Now remember, I said I'm not interested in f derivative squared. What's the reason for this? Well, because if you have a number less than 1 and you square it, what happens? It gets smaller still. So, in any case, when I'm multiplying together two small numbers, I don't consider it big enough to be important in the estimation, right? Now, f derivative, we've already stated that this is a small number. It's between minus 1 and 1, so I'll just write in here small number. Now let's not forget what we're looking for. What are we trying to find? Fixed point. And what is the formula at the start that we were trying to solve? fx equal to x. So if fx is equal to x, then we're trying to get fx minus x equal to 0. So as long as we're close to the answer, what do you think the value of fx minus x will be? What type of number? Well, it should be a small number because you're trying to get closer and closer. So as you use the formula more, this difference here gets smaller and smaller. So as long as you start, and this is actually also important, as long as you start near your fixed point, then fx minus x should be a small number. Okay, so what I'll do is I'll also make a condition at the start where we'll start near our fixed point. That is, now I'll call the starting value x0, but remember in the definition I used x0 to mean the fixed point, the answer. So don't get the two confused, okay? x0 here for me is meaning the starting guess. So I need fx0 I need it to be near x. So I'll say fx0 minus x0, well, no, not x0, no, I know what, I'll just say fx0 is approximately the fixed point. In other words, we should start near the answer. Now, of course, you don't know what the answer is, because if you knew the answer, you wouldn't be doing this to begin with. But you at least need to start near it. So you need maybe a graph or something to make a good guess at what the fixed point is. Okay? So if we start near the answer, then we're multiplying a small number by a small number, which we'll say will be quite a small number. So what can I do? I can drop it. So I get then this result. Oh, what's gone terribly wrong here? Got these. Okay. Now, we have the answer. Look how small that formula is, and how strange it is.
Wouldn't it be x n minus n plus 1?
Yes, it would be. Thank you. Now, look how small that formula is, and how strange it is. Basically, what I'm telling you is the way you can find a fixed point of a function is actually to use the function itself to get you closer and closer to the answer without making any change to it. I don't know, that seems kind of strange, but if we look at an example, we'll see how it works, okay? But anyways, we have the answer here. We have the very neat small formula, xn plus 1 equals fxn. So you'll need to make note of this. So this is called this is the process to find the fixed point. So maybe that's important enough to get its own box as well. Okay. Now, I just put the result there in a box there. To find the attractive fixed point of f, we use the sequence xn plus 1 equals fxn. And this is to find the attractive fixed point. Now, I haven't actually said the difference between attractive fixed point and fixed point. And it's better I show you with an example the difference. So I actually decided to deliberately leave the sentence open at the end there. The point that we find is the attractive fixed point, but. So the but now is going to be an example to show you just the care you need to take between attractive fixed point and fixed point. Because they're actually two different things. So with the first example I gave you, I'll show you the difference between the two. Okay? So can I go onto a new page to show you this example? Yep, okay. So what was the example I gave you at the start?
X squared.
Yeah, x squared. So we have fx equals x squared. Now let's try our process. So what did we say the answer was? A 0 or 1, okay? So let's start at, for example, 0.5. So if I start at 0.5, I'm saying my first guess, x0 equals 0.5. Now, how do I find my next estimation? What do I do? Yeah, so I put 0.5 back into the function. So what's 0.5 squared? Yes, 0.25. Okay, and then I put it back in again, and I get, I think, 0. No, that's half it. It'd be one, it'd be 1 over 8. Yeah, 0.125, wouldn't it?
I think so.
It's a half squared, which is a quarter. No, 1 over 16. Okay. Let's forget about decimals now. Right, so 1 over 16. And then I put it in again and again and again. And what's happening? It's getting smaller and smaller and smaller. So what number is it moving towards, converging to? It's 0. Okay? So etc., etc., etc. Etc., etc., etc. We conclude that the attractive fixed point is 0. Right, now, there was another fixed point. What was the other fixed point? 1. So let's start at a number close to 1. Let's say something like 1.5, 1.5, 3 over 2. So let's do that now. x0 equals 1. Let's stick with fractions. 3 over 2. So what would x1 equal? 9 over 4. And then x2 equals 81 over 16. Yes. And then let's do one more. x3 equals, oh, maybe let's not do one more. 81 squared over 16 squared. Would somebody be so kind as to calculate that? Yeah, just do it out in your head there real quick. Yeah, give us the decimal afterwards. 0.8 ish? No, definitely not.
Oh, no, of course not.
Just change.
It's 6 point something.
Oh, what's taking so
Decimal,
long?
right?
Yeah, the number, yeah.
Isn't that what we're getting right there?
Yes, that's right. 25.6289, blah, 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 blah.
How's that getting us our answer?
Yes, that's right. This is the problem. What were we expecting to get? 1. And so why didn't I get 1? Why am I moving away from the answer? Why am I not moving towards the answer here?
Isn't it the thing that f derivative of x should be?
Yeah, well, it's possible that the derivative is not less than 1. Let's do a quick check. What's the derivative of x squared? 2x. And I started at 1.5. So what's 2 multiply 1.5? 3. Is this less than 1? No. So in fact, the formula doesn't always work. Like we said, you need the derivative to be between minus 1 and 1. Okay? So it doesn't work here. But 1 is an answer. But we couldn't find it from the formula. And this is exactly the difference between fixed point and attractive fixed point. Okay? Attractive fixed point is when it's possible to get the fixed point from the formula. Okay? So fixed point and attractive fixed point. You could have a fixed point and you might not be able to find it because it's not attractive. like in this perfect example here, 1 is a fixed point, but I failed to get to it. So in this example here, it's a very simple example. It has 2 fixed points, and it demonstrates the 2 differences. The first one is attractive, the second one isn't. So I'll write that down for you. This simple function has 2 fixed points. The first fixed point, that's 0, is an example of an attractive fixed point, because the formula brings us to it. Okay. The second fixed point is an example of non-attractive fixed point, but still a fixed point, or perhaps an ugly fixed point if you want to think about it like that. Yes, maybe one person got that. All right, and this is a good example of the difference between the two. What I just think is very interesting about this is how simple the formula is. The formula is just the function itself. Okay, but the problem is this simple formula doesn't always work. Okay, in the exam they usually care about just the attractive case, so you don't have to worry about finding the non-attractive fixed point. Okay.
What do we do with that cos x? How do we?
Yeah, so let's go back to the cos x as an example. All right, cos x. So can you put your calculator in radians mode, and let's try cos x. So fx equals cos x. All right. x0. Now, if maybe I'll draw one of my beautiful pictures here. Paint. Okay, so we'll try and draw cos x roughly. Yeah. Right. Okay. X-axis. Y-axis. Well, actually, maybe I can use this thing. Yeah. Oh, no, hang on. Close enough. Close enough. Right, so this is our cos x. Now let's just think about the equation cos x equals x. Think about that as 2 curves. Y equals cos x and y equals x. If I have y equals cos x and y equals x, I put the 2 together, what do I get? If y equals cos x and y equals x, or let me say it another way, cos x equals y and y equals x. So what can I say about cos x? Cos x equals x. Yep. So you can also think about a fixed point as trying to solve the equation y equals cos x, which is this graph here, and then what's the graph y equals x? It's just a straight line. What's special about it? Straight y equals x, what type of line is this? Well, it passes through the origin, and what's its slope? 1. Yeah. So the line would look like this maybe. So, oh, look what I did. Why didn't anybody correct me? That's not cos x. Yeah. Now look, I have to undo this hard work now. That was sine x. Okay. Now which way do I need this? Cos x goes down.
Maybe it goes down, up, like.
Yeah, but how am I going to draw
So
this?
put
With
a
the
straight. See, what are you doing?
I don't know what I'm doing.
See,
All right.
just put a straight line on top,
Just
and
throw
then
it.
just bring the curve all the way down.
I'll
like
just
that.
use pencil. All right.
You could have used the curve.
It's fine. It's fine. There.
Better than yesterday.
It's better than yesterday's. Yeah. All right. So there's cos x, and then here's the other one. Y equals x. So if I have a look here, the fixed point is actually this point here. So at what point does cos x cross the axis first? What angle here? When is cos x 0?
Pi over
Pi over 2. So just a very rough guess here. If that's pi over 2, that's 90 degrees. What do you think this angle is about, roughly?
Pi over 4.
Yeah, maybe like 45.
Yeah.
Pi over 4. Maybe a little bit more. So what we'll do is our first guess, we'll try pi over 4. So can you tell me pi over 4? So can you just type that in and tell me what that is as a decimal? So 3.14 divided by 4. 0.7. So let's just start with 0.8. Make it easy. Okay? Can you now tell me what cos of 0.8 is? Make sure your calculator's in radian modes.
Cos of 0.8.
Yeah.
That's 0.696.
Okay. 696. And then, can you tell me then, we'll do it 3 times. So we'll do it again.
Oh, so I have to take the 0.
Yeah. So just do cos answer.
Okay. Okay, then we get 0.767.
767. And then do cos answer.
We get 0.72.
Okay. Okay. One more because now I'm curious.
We get 0.752.
Okay. So, what do you think we're kind of moving towards? We're kind of moving, I think, to 0.725. Would you say? Yeah, go on. One more.
0.730.
Yeah. 0.730. Okay, so yeah, we're thinking maybe something like 0.725. Let's open up derive and see if we can get the answer. Because this is the first time you'll see derive being used, yeah? Okay, so derive can solve equations for you that perhaps you can't. So we don't need this anymore. Discard. Alright, so let's type in our equation. Cos x equals x. Let us shrink it down so you can see it actually. Oh, come on, where's my little arrow? Alright. Okay. Cos x equals x. Solve expression. Numerically, real number. Solve. And there's the answer. 0.7390, etc. So you can see the method was quite good. We got pretty close to the answer pretty quickly. Okay, and that's all there is to say about attractive fixed point. So you get this in the exam. It came up, oh yeah, it came up this year, and actually nobody got the question right. So I want to show you, well, I'm picking out the difficult one. So I want to show you the type of question that they got and how they couldn't figure it out. So let me show you what they got. I really hope this is still recording because my little box has disappeared. You know the box I had around, oh well. Alright, let me show you the example. And I think what confused the students was it was a fixed point problem, but they didn't want the fixed point, they wanted something else. So I can't remember the exact question, but it was something like this. What are the 4 formulas to find the attractive fixed point of this function? It was something like, I don't know, x cubed plus 10x squared maybe minus 1, something like this. I can't remember exactly what it was, but it was something like this. Okay, so they don't actually want to know. They don't actually want to know the formula or the solution. They want to know the formula. Okay, so firstly, you have to state this as attractive fixed point problem. So basically, you're trying to find when your function is equal to x. Okay. So in this case, it's when you have that whole thing. No, I don't think this was the exam question. Let me think, what was the exam question?
Just go get from the office.
Yeah, I remember now. No, it wasn't like this. They phrased it differently. What are the 4 formulas for finding the root of x cubed plus 10x squared minus 1? Yeah, that's how it was. Now what's... Oh, and the other thing is, you might think that, well, what's one formula you could use to find the root of something? We did yesterday, Newton-Raphson. But they rather annoyingly said Newton-Raphson is one way to find the root. What are the 4 other formulas? Okay. And I think this really threw a lot of people. And to be fair, this question rather annoyed me because it's not really on the syllabus, but it came up. So in case it comes up for you, I think it's important that I show you what they wanted you to do here. Okay, so we've just ruled out Newton-Raphson. So how many methods do we have left? Well, we just have one really. It's fixed point. But what's the problem here? It's not really a fixed point because what are you trying to do? You're trying to solve this equation. And that's not, it's not a fixed point. It's a root. So how could I make this into a fixed point problem? Does anybody have any ideas of changing this into a fixed point? Now you might say, okay, well I'll just bring the x over to the right, but what's the problem here? In this cubic, there is no x. There's only x cubed and x squared. And this confused people as well. It's like, well, where's the x to bring over to make it a fixed point problem? So what do you think we could do here? Well, there's still x's in it. We just have to do a bit more work. So what you would do is, one possibility is you bring the 10x squared over. So it becomes minus 10x squared. Yeah? And then what would you do? Well, you could then divide by minus 10. So you get this result. And then what could you do next? Square rooted. And now I've changed my root problem into a fixed point problem. And in this situation, what is the function? That's root thing, yeah. Now, I don't really like the way the minus 10 is, so I'll bring the minus up to the top. And I have this result. So if I was writing this out as a formula, the formula will be x n plus 1 equals the function itself. that would be one formula. You see? So that was one way to make a formula, but they said 4, so I need 3 others. So who can think of another way to manipulate this formula to change it into a fixed point one?
Use the x cubed.
I could use the x cubed, bring it over. So then what would I need to do then? Well, let's have a quick look. I won't do the whole steps. I bring the I'll bring these 2 over to the right. So I get on the right 1 minus 10x squared. You see there? And then what would I do? Cube root, and that's another formula. So that's another fixed point. Well, that's 2. 2 down, 2 to go. Yeah, what about the other 2? Yes. What about the other 2? Oh, very good. Continue. Yes, what's the common x here? X squared. So if I take that x squared out, so I have here x squared, and then 1 plus 10x.
No.
No.
X plus 10.
Yeah.
What did I do wrong?
X
X, plus,
X plus 10.
oh yeah, x plus 10.
I want to see it.
Yeah, come on, wake up. X plus 10. Yeah, on top of it. Right, x squared times x plus 10. Then what would I do next?
Bring over the 1.
Yeah, bring the 1 over. And then this is where I have 2 choices. I could bring the x plus 10 down to the right. And then what would I do next? Square rooted. Or, what could I bring down? X squared, and then just take the 10 over.
That's 2.
And that's the other 2. So hence I found all 4. Now, you must understand, this was question 2 in section A of the exam. Yeah. And you know what the average score was? 0. Everybody got 0. Yeah. Because it happens. You know, sometimes you get something that you haven't seen in a past exam before. Okay? And I don't think there's an example like this in your workbook. So it's just one of these situations whereby you really just need to be thinking on your feet. Because as you see, what I did there wasn't very difficult. But you just need to be focused, you know, really have to use your creativity. And these types of questions are the questions to distinguish the A star from the A. The very best from the best. Okay? That's the purpose of these types of questions. Now you don't, like this is only one question in the exam. You know, the rest of the exam was okay. But you know, there's 1 or 2 questions like this where it's just to make sure you can pick out who are the top. Okay. I think that very, very much covers fixed points, attractive fixed points. It covers it probably more than what the syllabus requires. But I think after this now, you shouldn't have any problems with them. Because in fact, the syllabus doesn't say anything about mentioning when it doesn't work. You know, the syllabus says you don't need to mention when the fixed point doesn't work. But I think it's important to know when the formula doesn't work. Okay? Just like with Newton-Raphson too. Okay, so I want you to try, the questions aren't so difficult in the workbook. It's mostly practicing with your calculator. And some people might get different answers because the formula only gives you one answer. So it depends where you start and what answer you get, okay? But mostly I just want you practicing the formula. Okay.